Welcome to Fred
and Amy's Math Shack.
Hi, to start today, I'm going to get you to do a few revision questions of previous topics in A-level maths. Now, these questions are actually from an old specification that was non-calculator, so I want you to do all of these, actually, I just realized, except number 5 without a calculator. I put 6 and 5 the other way around just in this case, just in case you're running short of time, then make sure you do number 6 and leave number 5. But ultimately, I'd like you to try them all. I'm going to show you the mark scheme for this, which is underneath. And then I'm going to go through each one. So you can pause the video and check this mark scheme, otherwise watch on for more explanation. Here it goes. So we need to remember that a minus in a power means 1 over. So this becomes 1 over 11 squared. And 11 squared is 121. So that's our answer. Meanwhile, here we've got to remember that actually we're dealing with fractional powers. Now, first of all, we can write this like the following. It's 100 to the power of a half, all to the power of 3. Because when you use your rules of powers, you just multiply those two together. So we're sort of doing the reverse. Why would we do that? Because 100 to the power of a half is actually the square root of 100. Square root of 100 is equal to 10, so it's 10 cubed or 1,000. Here we're expressing it in a different form. Essentially, this is a rationalizing the denominator question and a simplifying surds question. So root 50, we can write that as root 25 times root 2. I've kind of done 2 steps in one. And then this one here, 6 over root 3. I want to rationalize the denominator, so it's going to become 6 root 3 over 3. I've done that quite quickly. I've timed the top by root 3 and the bottom by root 3. This then simplifies quite quickly actually to 5 root 2, because root 25 is 5, plus 6 divided by 3 is 2, 2 root 3. And we've got it in the form a and b are integers. So that was a bit of indices and a little bit of surds. Question 2 is a completing the square question. So the first thing to do is to factorize out a 2. X squared minus 6x. I divide that 12 by 2. Don't worry about p, just put it here. But remember, it is equal to this thing on the right. I'll bring that in a minute. Now I'm going to complete the square on the inside. So it's going to be x minus 3. We have that 6. And then we minus 9. We minus that thing squared. If you expand this out, you would get back to x squared minus 6x. I'm not going to go into any more detail on that now. If you don't understand that, then look back at completing the square. There's lots of videos on that and so forth. Still need to plus the p. I then expand this back out. It's going to be 2 times minus 9, so minus 18 plus p. And we've got it in the right form. So I can see that q is going to equal 2. R is going to equal 3. And then to get plus 10, I'm actually going to have that p is equal to 28. Essentially, I've set minus 18 plus p equal to 10 and then solved it. Simultaneous equations. We're actually, we've just done a lesson on that in theory. This is a lesson afterwards. So how'd you get on with this one, I wonder? Bit awkward, I'd say. Best, I think, to make y the subject here. Y is going to equal 2x plus 1, and then substitute that in. So I'm going to substitute that in for this y here. So it's going to become, it's not so bad actually, it's going to become x squared minus 3 lots of 2x plus 1 plus 11 equals 0. And I've substituted in and got rid of that y. So x squared minus 6x minus 3 plus 11, it's going to be plus 8 equals 0. This will factorize x minus 2, x minus 4 equals 0, x equals 2, or 4. I always like to then put it together. You could do x1 equals 2, x2 equals 4, but I'm going to do it like I normally do it. When x equals 2, y equals 5. I've put it back into here. This is the simplest one to put it back into. If you got time, you could substitute it back into this one as well, but I'm not going to do that. When x equals 4, y equals 9. And there we have it. Brilliant. Okay, number 5 is this trig question. Got to first of all go from this one here to this one here by proving it. So let's start with sine theta. And because there's no sines or causes, sorry, sines or tans in the answer, I think the first thing to do is just get rid of that tan. Write tan theta as sine theta over cos theta. They are equivalent. And that's going to equal cos theta plus 1. And there's no fractions in the answer, so I think a good shout is to multiply through by cos theta. And this becomes sine squared theta, because the cos squared theta just goes, equals cos squared theta plus cos theta. I've multiplied through by cos theta. This is looking good now. I've got another identity I can use. Let me write it over here. Sine squared theta plus cos squared theta is identical to 1. So that means sine squared is identical to 1 minus cos squared. And I can write this down here. I'm going to write it in full. 1 minus cos squared theta equals cos squared theta plus cos theta. And I'm basically there. I can rearrange this to 2 cos squared theta plus cos theta minus 1 equals 0, which is what was expected. Brilliant. If you couldn't do that, you can actually still get these 5 marks. Hence, solve this equation. Well, actually, we don't want to solve that equation as it is. We want to turn it into this. So they've actually helped us out. Given all values of theta between 0 and 360 degrees. Okay. This is in fact a hidden quadratic. You could, maybe I will do this, you can do a substitution, t equals cos theta. Or you could just factorize directly in terms of cos theta, but that's going to mean that 2t squared plus t minus 1 equals 0. And I'm back to solving a quadratic, which I suspect will factorize, because, yeah, it does. It's going to be plus 1 here, minus 1 here. T equals a half, or minus 1. And remember, we can bring it back. Cos theta equals a half, or minus 1. And now we've just got to find out theta. So we can do most of this without a calculator. Just this last little bit, actually, you could in theory do this without a calculator, because the values are nice. Depends if you know your exact values of cos and sine and tan. So cos looks like this. And the first value of theta, which is inverse cos of a half, if you put this in your calculator, is 60 degrees. And that would be basically finding out where it's equal to a half. And I've just found this one here. If I want to then find this one here, I can use the symmetry of the curve. It is kind of symmetrical about this line here, or about the 0, but essentially, if this distance is 60, then this distance is also 60. And this here is 360, because that is the period of cos. So the second one is going to be 360 minus 60, 300 degrees. Or theta is going to be inverse cos of -1. There's actually only one value in the range we're interested in, and that is here. It's going to be 180 degrees. In fact, we can do all these questions without a calculator. Let's keep going, we've got one more. Calculate the discriminant of -2x squared plus 7x plus 3 and hence state the number of real roots. Okay, the discriminant is b squared minus 4ac, where I'm assuming you know what a, b, and c are. They're the coefficients in the quadratic. So it's going to be 7 squared minus 4 times -2 times 3. And that's going to be, oh, let me do it down here. That's going to be 49 plus, because there's a double negative, 24, which equals 73, which is greater than 0 to, and I'm going to say distinct real roots. If it equals 0, technically there's 2 identical real roots. So I think it's good to, I will check the mark scheme in a second, but because I don't know if they just give you it if you write 2 real roots. Let's check now. So number 6. 2 real roots you get away with. You don't actually have to say they're distinct. 1 mark for the discriminant and 1 mark for the statement. But anyway, I've done a little bit more. That's okay. Right, and then we're told that this quadratic has equal roots. Find the possible values of p. Sorry, that was part 1. Part 2. Right, for equal roots, we get b squared minus 4ac equals 0. So we're going to get p plus 1 squared, that's my value for b, minus 4 times 2 times 8 equals 0. P plus 1 squared minus 64 equals 0. And there's a few ways we can do this. The best way is actually just going to be to write p plus 1 all squared equals 64. This is what you do when you complete the square. We've actually got it in completed square form here. So p plus 1 will be plus or minus the square root of 64, which is plus or minus 8. Does this say any specific kind of possible values? So there's going to be 2 values. P is equal to 7 when we have 8, or minus 9 when we have minus 8. Hope you're happy with those. Good start. Previously, we've studied the discriminant of quadratic equations and seen how that tells us information about the number of roots. We've also looked at quadratic simultaneous equations, where you have 2 functions and you're interested in where they intersect. And one is a quadratic. Today, we're going to be looking at combining the 2 topics, looking at the discriminants of, or not of, but from quadratic simultaneous equations, and seeing, therefore, how many solutions to the simultaneous equations there are. I think an example will make things the clearest, but essentially we're gonna find out about these solutions. The first thing we do is combine the equations and then calculate the discriminant. So we're gonna substitute in here, or set the y as equal to give a quadratic. X squared plus 10x equals 4x plus 1. Now I'm going to do what I normally do, set this quadratic equal to 0. So x squared plus 6x minus 1 equals 0. Now this resulting quadratic doesn't really have a sort of a physical meaning in the same way that we have with the graphs. However, we know that the solutions to this give us the solutions to the x solutions in the simultaneous equations, and from that we can get the y solutions. But the result is that if we know if we can work out how many solutions there are to this quadratic, then we can know how many solutions there are to the simultaneous equations, and that's the key thing. So if we look at the discriminants of the resulting quadratic, it will tell us how many solutions there are to the simultaneous equations, which can be useful. So let's have a go here. So b squared minus 4ac in this case is going to equal 6 squared minus 4 times 1 times minus 1. And that's going to be 36 plus 4, it's going to be 40. So my discriminant of my quadratic is 40. This is greater than 0. And there will be two distinct real roots to the quadratic. And therefore, there will be two distinct solutions to the simultaneous equation. So combining the two aspects of this topic. I'm not interested in what they are. I just know that there's two of them. Try this one yourselves, see what you find out. So again, we can set them equal to one another because we've got y as a subject already. Now I recommend making x squared positive. I just think it makes life easier. So I'm going to get all these onto the right hand side and then just swap it around. And then again, I've got a resulting quadratic, so I'm going to find the discriminant. It's going to equal minus 2 squared minus 4 AC, which is 4 minus 4, which in this case is 0. So here there's going to be two identical solutions. Just like we had two identical roots to the quadratic. Okay, nice. Try these two other ones. So here it's going to be the same kind of deal. So 2x squared, I can actually cancel the x's out. 2x squared plus 1 equals 0. It's going to equal, okay, in this case, there is no b, actually. So it's going to be 0 minus 4 times 2 times 1. And that's going to be minus 8, which is less than 0. There's going to be no real solutions. And finally, I thought I'd put one in where you had to do a substitution into it. X squared plus, and then I'm going to replace this y by this thing here. Expand this bracket, I'm going to get 16 plus x squared minus 8x. I've just expanded a double bracket quickly in my head, equals 8. If you need, if you want to take it more slowly, write it like 4 minus x, 4 minus x. Don't forget that's what it means. Okay, what to do now? So we're going to get 2x squared minus 8x plus 8 equals 0. And this is another one where we get two identical solutions. Or equal. Okay, I hope you're happy with that. A little extension, if you're up for it, is can you sketch each pair of curves on separate axes? Just a sketch using the information that we now have. So here's the first one. Right, let's give this a go. So just a quick sketch. I'm going to sketch the quadratic to start with. Now I could factorize this as x plus 10. And that will give me my roots. It's going to go through 0, and it's going to go through minus 10. And it's going to look like this. I'm not going to label them here. It's only a quick sketch. And then 4x plus 1 is going to go through 1. And it's going to look a bit like this. But we are going to see that there are two solutions. So maybe I should have it a slightly more of an angle just to illustrate that, because nothing's to scale here. But it's going to roughly look like this with two solutions, one here and one here. Okay, nice one. How about this one? This one is you have to remember how to factorize a negative quadratic. So I would take the minus out. And it's going to become x minus 2, x minus 3. So it's the roots are going to be 2 and 3. And the quadratic's going to look a bit like that. I've then got 3x minus 5, and I'm interested in drawing it. Well, we know there's two identical solutions. Essentially, it's just going to touch the graph once, and it might end up looking a little bit like this. There we have it. So you can see the difference between two distinct solutions and two identical solutions. Here we had no real solutions, but I'm going to try and sketch the quadratic like reasonably well. So this factorizes to 2x and x plus 1 minus 1. So we get a solution of minus 1 and a solution of a half. And then we've got x minus 2, but we know that it misses the graph, so it's probably going to look a bit like this. There we have it, there's our sketch. Okay, these are my challenge questions, but I'm hoping if this is making sense. I purposely chose the quadratic so that they could be sketched and practicing previous skills. So the last one, well now I'm going to draw the bottom one first. This is actually a circle with center the square root of 8. It's centered at the origin, sorry, radius square root of 8 centered at the origin. It's going to look like that, roughly. And then we've got y equals 4 minus x. We can see that there's two identical solutions. So 4 minus x is probably going to come down and touch the graph a bit like that. And actually, this gives us a tangent. We're going to use this knowledge in a minute. Okay, good. This is the key bit of the lesson, really. Understanding how the discriminant affects the graphs. I do think showing the graphs helps you see what's happening as well. So, overall, for a pair of simultaneous equations that produce a quadratic equation of this form, if the discriminant is greater than 0, we get two real solutions. Either looks like this or like this, depending if it's a happy or a sad quadratic. Now I actually disagree with this. It says one real solution. I don't actually like that. I'm going to change that to two equal solutions. That's what I've been using elsewhere. So in this case, it just glances off, and actually these would all be tangents. We'll be looking more into that. Okay, it's just something I'm going to throw out today. They are lines that glance off, touch at one point, they are tangents. And then if b squared minus 4ac is less than 0, we get no real solutions and things like this. So now we're going to use that knowledge to help us out in cases where there's unknowns in the equation. So we've got a function and it doesn't intersect this function. Find the possible values of k. So I want you to have a go at this. You can even have a go at all three, and I'm going to go through them. Right, here goes. So I'm going to substitute in for y. It's going to be x squared minus 2x plus k plus 4 equals 4x. Expand the bracket, x squared minus 2x minus k plus 4 equals 4x. X squared minus 6x. I'm going to write it as plus 4 minus k equals 0. Now this is my constant, so I'm just going to put it in a little bracket because I need to see clearly that I've got my a. This is a, b here, and all of this is c. So I know for it to not intersect, we're going to get b squared minus 4ac is less than 0. And that means I'm going to get 36 minus 4 times 1 times 4 minus k is less than 0. And I've created an inequality to solve. 36 minus 16 plus 4k, expanding that bracket, is less than 0. So I'm going to get, this is equal to 20, I'm going to get 4k is less than minus 20, and hence k is less than minus 5. Oh, good question. So does that make sense? I'm not going to sketch it in this case. I can see that I'd get a quadratic. It kind of makes sense. I'm going to have a quadratic, and then there's going to be a certain point where all these values, my k is my constant. So if I make it more and more negative, it's going to go sort of down the page. All right, next one. Prove that 3y plus x equals 20 is a tangent to x squared plus y squared equals 40. Now, I've kind of already mentioned this. Tangents, we've had a tangent here when the discriminant was equal to 0, and I even spoke about it here. So essentially, this is code for we need to show that the discriminant is equal to 0. And we can do that by substituting in. It makes sense to substitute in for x. So x is equal to 20 minus 3y. And then let's substitute that in. 20 minus 3y all squared plus y squared equals 40. That's going to give me 400 plus 9y squared minus, we're going to get a minus 60y and another minus 60y, so 120y plus y squared equals 40. 10y squared, it doesn't like lots of large numbers at the moment, but let's stick with it. 10y squared minus 120y plus 360 equals 0. I would, before I do anything with the discriminant, I would personally divide through by 10. Y squared minus 12y plus 36 equals 0. B squared minus 4ac equals 144 minus 4 times 1 times 36, and that will equal 0. And that is enough, really. So 3y plus x minus 20, sorry, equals 20 is a tangent. I don't think I need to say any more. I think there's like enough. It just touches. I think that's enough. Okay, one more. Give this a go. So now we're told that, I suppose that's another way of saying it meets at exactly 1 point. Maybe I'd take this, but yeah, I'm not happy with the one real solution, but it's okay to say that it meets at 1 point. Subtle difference. So I'm going to substitute in. We've got kx squared plus 2 lots of 2x plus 1. I'm running out of space. Plus k minus 2 equals 0. So I've just taken this equation and substituted in for y. Kx squared plus 4x plus 2 plus k minus 2 equals 0. This is good. These are going to cancel. So I've got my a, my b, and my c. So 4 squared minus 4 k times k, 4k squared, is going to equal 0. So 16 minus 4 k squared equals 0. 4k squared equals 16. K squared equals 4. K equals plus and minus 2 by taking the square root, but it does say that k is a positive constant. K equals 2 since k greater than 0. Okay, and that's it. For this value of k, find the coordinates of intersection. So now we just need to go back. This is going back to what we did right at the start of simultaneous equations. Okay, so we're going to get y equals 2x plus 1. And actually, I've just realized I don't need to do all this because I've already got my quadratic. So actually, it's going to be 2x squared plus 4x plus 2 equals 0. I don't need to do the whole thing again. I'm just substituting my value of k into the quadratic that I had when I combined them when it was in terms of k. Divide through by 2. And this factorizes really nicely to x plus 1 squared equals 0. So x equals minus 1. I can't believe I'm going to fit this in. Substitute the minus 1 back into the original, one of the originals, so into here. So 2 times minus 1 is minus 2, plus 1 is also, that's going to be minus 1. Y is minus 1. Okay, and there we have it. That's our answer. So make sure you can deal with this kind of question, that you can still solve simultaneous equations, but you're able to cope with the discriminants. Okay, do some more practice, but that is our lesson today. I hope it will make sense. Well done.